at Concordia University in Montreal, Canada, studying how Arctic bacteria are changing and evolving with climate change. And I'm really happy to be moderating this next session. So welcome to Permafrost Day. This is a whole day program where we'll be covering the local to global implications of thawing ground across the Arctic permafrost region. The latest studies confirm that the Arctic is warming 3 times faster than the global average. This rapid warming is driving an equally rapid pace of change across the Arctic, including changes to that affect permafrost or the permanently frozen ground that underlies much of the region. In this session, we're going to cover some of the latest developments in efforts to understand what's happening to permafrost systems and what the implications are for global climate. To set the scene, we'll hear an introduction to the relationship between permafrost thaw and climate from Dr. Sue Natali, after which Dr. Brendan Rogers will speak about wildfires and its impacts across the permafrost region. Dr. Rachael Treharne will speak about abrupt permafrost thaw, and finally, Dr. Gustaf Hugelius will take us off land and talk about subsea permafrost. So really happy to welcome our speakers to the floor. Thanks.
All right. Thank you, everyone, for being here. My name is Sue Natali. Both of them? Okay. Better? Yeah. My name is Sue Natali. I'm an Arctic Program Director and Scientist at Woodwell Climate Research Center. And I guess there's 2 main messages. I'm going to be providing an introduction to permafrost thaw. The 2 main messages I'd say of the entire day is that the risks of climate change are a lot higher when we account for permafrost, and that people are being severely impacted now as a result of permafrost thaw. So this is not a problem of the future. Woodwell Climate Research Center is a research organization in Massachusetts and the United States on the land of the Wampanoag people. We conduct our research across the northern Arctic and boreal regions. Permafrost underlies much of these lands. The focus of this session is on climate impacts on permafrost, but I want to acknowledge that we recognize severe impacts of climate change on Arctic land and people and water, and that these climate changes are impacting and are interacting with ongoing human harms caused by colonization and extractivism. As scientists, we continually aim to conduct our research in more equitable ways by valuing people, indigenous knowledge, and indigenous sovereignty. All right, so sorry, I had forgotten to switch the slide. So the Arctic has warmed 3 to 4 times faster than the rest of the planet. You can see that in this map, this very red area, northern regions. And each year in the Arctic, as with many other places, we're seeing a record, breaking a record, breaking a record. So the Arctic is already beyond 2 degrees Celsius warming. As a result of that warming, the once frozen ground called permafrost is starting to thaw. So permafrost ground is defined by its thermal state, so ground that's frozen for 2 or more consecutive years. And that ground can contain any material, so it's essentially soil with a lot of organic carbon in it, often has a lot of ice. Any of the material that's below 0 degrees Celsius, once it thaws, it's no longer a permafrost. When you have a lot of ice in the ground, as you can see in this example from the Peel Plateau in Canada, the ice turns to water and then the ground collapses. So this is a map of the permafrost region. Permafrost underlies about 15% of the Northern Hemisphere land area, but much of the permafrost will be lost in the coming decades. Here showing projected near-surface permafrost loss in 2100 under RCP 8.5. And And I just want to point out two things about this figure here. So the projected loss in permafrost over the next century is about 25% to 70%. So that wide range is driven by the decisions that we make now. So this doesn't have to be the future of the Arctic. The other thing I want to point out is that permafrost thaw is already underway. So this has been happening. And as a result of that, communities are being severely impacted, as we heard from this last panel. When permafrost thaws, you can have these catastrophic ground collapses, as you saw in that previous photo. But you can also have more gradual thaw that maybe you're not seeing a collapsing hill slope, but this is impacting communities that are living very close to sea level. And as a result of this gradually sinking ground, these communities that are surrounded by water are losing more and more land. This can have, at times, disastrous impacts of communities that are often living in very vulnerable environments. And this affects the permafrost thaw is interacting with sea level rise and erosion. You can see from this example, this airstrip here, many of the communities in the Arctic are not accessible by roads. In this case, the only way in and out of this community is by this airstrip, which is really like just meters away from being lost. The other reason that we're here is because the global impacts of permafrost thaw. So permafrost stores about 1.5 or 1.4 to 1.6 trillion tons of carbon. So that's about twice the amount of carbon that's currently stored in the atmosphere. There's very likely another trillion tons that's stored in deep sediments that's not considered in that first more constrained estimate, and also in subsea permafrost, which we'll be hearing more about. This carbon is in the form of organic matter. Once that organic matter thaws, then microbes can break it down, releasing it to the atmosphere, leading to more warming and more thaw. And so this is this positive feedback where permafrost thaw can lead to more warming. The big question is how much carbon will be released from permafrost? How fast will that happen? Will it come out in the form of carbon dioxide and methane? And you'll be hearing more about that in the subsequent talks. But I just want to say here is that carbon emissions from thawing permafrost by the end of this century will very likely be substantial. There is a wide range of estimates right now, but even at the low end, carbon emissions are on par with some major fossil fuel emitting countries. On the high end of our scientific estimates, the emissions from permafrost thaw by the end of the century may be larger than emissions from the United States, the second largest greenhouse gas emitting nation. The other problem about this is that our current global climate policy isn't fully accounting for emissions from permafrost thaw. And as a result, the targets that we're setting now, our global carbon budgets to remain below 2 degrees Celsius, are fundamentally inaccurate. They're accounting for some level of permafrost emissions, but they're not fully accounting for it. And just a quick review of permafrost in the IPCC's sixth assessment report. What the IPCC says, there's high confidence that warming will cause more permafrost thaw. There's high confidence that thawing permafrost will lead to carbon release. Already some permafrost regions are a net source of carbon. So what that means is this northern region has been accumulating carbon for tens of thousands of years. Plants are taking it up from the atmosphere, storing it in the soil, being frozen in permafrost. There are some locations that are already starting to switch. So carbon dioxide and methane is being released to the atmosphere. The IPCC says permafrost carbon losses are irreversible on centennial timescales. Yet there still is a lot of uncertainty on the timing, form, and magnitude of emissions from permafrost thaw. There have been some advances in permafrost science and its representation in the IPCC reports. The last report, AR6, is the first time that permafrost carbon was included in IPCC models. So these are the Earth system models that are informing the science. However, 82% of the IPCC Earth system models didn't even include permafrost carbon at all. The two models that did include permafrost carbon excluded some really important thaw processes, which you'll be hearing about in the next set of talks. The IPCC permafrost carbon budget reduction, and so there was an accounting for permafrost carbon in the last IPCC report, but it assumed a linear relationship between warming and permafrost thaw. As you'll hear more about in the coming talks, we know that's not how the world is currently functioning and very unlikely to function into the future. And as a result, the current estimates that are in the IPCC report are very likely underestimates of the permafrost carbon feedback. And I will end there and just say thank you, and we'll go to the next speaker, which will be Rachael Treharne. Thank you.
Thank you so much, Sue. And just to reiterate, thank you to everyone who's joining us for this session, both here in person and online. Hopefully I'll get some slides up in just a moment. But yeah, we've had a great introduction already to permafrost and to the importance of permafrost thaw from Sue. And my job, can go to the first slide. Yep, that's perfect. Okay, brilliant. Yeah, is just to make that landscape of what permafrost thaw means just that little bit more complicated, but just a little bit. So I hope you'll bear with me. So when we use the phrase permafrost thaw, the actual physical process that very often we're talking about is gradual thaw, and this was sort of alluded to a little bit by Sue. And what gradual thaw actually means is it's what happens when the warmer air temperatures that Sue highlighted, talking about how fast the Arctic is warming already, when those warm temperatures are gradually penetrating down into the ground, thawing the permafrost layer from the top down. And over time, essentially, you just have to go down deeper into the ground to be able to find that permafrost. I mean, this is the most widespread and is the most dominant process through which permafrost thaws, but it's not the only process. Permafrost can also thaw abruptly, and this happens most often in areas of the permafrost region where the ground contains a higher proportion of ice. I had a little video, but I don't think it's going to work. But essentially, what this shows is that when the ice within permafrost, ice-rich permafrost, melts, the ground loses volume. So what this video would show, if it was playing, is that what we're looking at here is three different permafrost cores. And there is one on the left, which is really peaty and organic, but also contains a lot of ice. And as that one thaws out, what we see is basically that the volume of that core really decreases. And actually, by the end of this clip, which I know you can't see, but the whole volume of that core has kind of collapsed. It's completely lost its structural integrity. And basically, it's gone from the height of that orange line on the left all the way down to the red line below that. Whereas the core on the other side of the screen, this is one that contains very little ground ice. And you can see that, again, throughout the clip, as it thaws out, it goes from the orange line at the top down to the red line. And you can see those lines are really close together. So essentially, we really see much less of that loss of volume. And the same thing happens essentially at a landscape scale. So instead of that sort of slow, gradual, centimeter by centimeter, top-down thawing of the permafrost table, we see this uneven subsidence, this uneven collapse of the ground surface as the permafrost thaws and the ice within that permafrost melts. And this is an example of the kind of feature that we mean in real life when we talk about abrupt permafrost thaw. So more specifically, this is a retrogressive thaw slump. And here, ice-rich permafrost has thawed, and in this case, the result is that a slope here is destabilized and slumped. And you can see all this really dark ground here. This is exposed organic matter that once would have been protected by that intact permafrost, but is now vulnerable to undergoing decomposition and therefore vulnerable to releasing that carbon that it has stored, perhaps for hundreds or thousands of years, back into the atmosphere. And of course, this looks like it is. It's a pretty dramatic landscape feature. But if we imagine kind of stepping back from this picture and thinking at a more regional scale, then these features are actually relatively small. But despite that, within this area, they can expose, as you can see, a large amount of carbon comparatively quickly compared to gradual thaw. So they can have sort of disproportionate to perhaps their spatial size, a significant impact on emissions across the Arctic. So there's still something to be concerned about from the point of view of climate. And in fact, perhaps the biggest reason to be concerned about abrupt thaw is that these are not well represented in climate models. We heard, I think, from Sue that few climate models include permafrost thaw at all. And by that, we mean that very few models incorporate gradual permafrost thaw. In fact, no climate models include abrupt permafrost thaw. This is something that is just not accounted for. So why is that? And there's a few reasons for this. One of the big ones is that we actually don't have a pan-Arctic assessment of abrupt thaw occurrence. So we don't know how much abrupt thaw is increasing in response to warming. We can be pretty confident and increasingly confident as new studies are coming out all of the time that warming is driving an increase in abrupt thaw incidence in many regions. Even some work has suggested in the high Arctic already. But we don't have a clear picture of the rate of that increase. And this is a pretty big challenge to overcome, again, partly because these features are pretty small. And in contrast, we're talking about the Arctic, the permafrost region, a huge region, much of which is remote or challenging and therefore expensive to access. And the result of that is that on-the-ground monitoring across the Arctic is pretty sparse. So this map is just showing monitoring stations across the Arctic that are recording both carbon dioxide and methane emissions throughout the year. So it's not all of the monitoring happening across the Arctic, but it does give you a picture of, when we focus on a specific question, how sparse that data collection is and how huge the gaps are where we don't have a really detailed picture of what is going on. And in the case of abrupt thaw, overcoming this becomes even a little bit harder, because in comparison, for example, to something like fire, where we can imagine there's a clear kind of thermal signature that we can use to find these things, abrupt thaw doesn't have a clear signal that it produces that we can identify remotely. So right now, being able to map abrupt thaw across the Arctic is a really major priority for permafrost science. And one really exciting approach to this challenge is being led by a colleague of mine, Woodwell Yang, who's working with Sue and also with Brendan, who's going to speak shortly alongside others, and has very kindly allowed us to tell you a little bit about this piece of work. So this is using a deep neural network model to map one type of abrupt thaw. And actually, that type is those retrogressive thaw slumps that we talked about earlier. And this is really brand new work. That means it's not published. And I can't pretend to be able to tell you very much about deep neural networks. Perhaps that's something that others can later. But I did want to give you a little preview of some of the results that will ultimately be published in this manuscript. So in all of these images that you're looking at here, there's two panels. The right-hand panel is showing a prediction which has been made by this new neural network model. So a prediction of where it thinks a retrogressive thaw slump is, with that prediction shaded in red. On the left of each panel, there's a reality check of the same area. So any confirmed retrogressive thaw slump being outlined in green. And the takeaway here is that you can see it's doing a pretty great job. You can see the same features that are outlined in green on the left being picked up in the red shaded predictions of the model on the right. It's not perfect. Looking at the pair of images on the right-hand side, there's a little tiny green outlined feature at the bottom of the water body you can see there, which it has missed. But overall, this is performing really well. This is a really exciting development. I would say, yeah, in my opinion, I'm really excited about this. And I just wanted to give this as a little taster of the real cutting edge work that is pushing forwards our understanding of what is happening in the Arctic. So I watch this space. At the same time, I and others in the community are kind of conscious that, as well as pushing forward this this real kind of precise, quantified understanding of exactly what it is that we're seeing in response to climate change across the Arctic, we need to be making sure that we're also kind of communicating and looking at the possible or the likely implications of the information that we do have. And that, of course, applies to Abrupt Thaw as much as to everything else. So this leads on a little bit to some of my own work, which is focused on integrating the existing knowledge that we do have, the existing work that has been done regarding Abrupt Thaw and other processes into this sort of simplified, pretty nimble climate model that we can use to look at questions related to global climate policy. In the case of Abrupt Thaw, my work with this model is building on this 2020 paper led by Merit Turetsky. And this is basically overcomes some of the challenges I've talked about by assuming that the rate of increase in Abrupt Thaw will track that of gradual thaw. So using that assumption to enable a pan-Arctic prediction, in fact, the first pan-Arctic prediction of future carbon emissions from Abrupt Thaw. So having built this approach into our own model, we've been looking at the impact, what the impact of accounting for Abrupt Thaw in this way has on carbon budgets associated with particular temperature targets. So what we're looking at here is an example of the reduction that we see in those carbon budgets. So on the left here, you can see the reduction in the carbon budgets for 1.5 degrees, and on the right for 2 degrees. And the bar on the left is showing that with respect to gradual permafrost thaw only, and the bar on the right is showing the increase in that reduction when you add in Abrupt Thaw. And you can see in both cases, it's a pretty substantial change in the size of that bar. And actually looking at the 2-degree target, that increase alone, we're looking at something that exceeds the emissions, global anthropogenic emissions for an entire year. So just for an idea of scale, we're talking about something pretty considerable. And I also wanted to highlight, particularly when we're talking about Abrupt Thaw, that it's not just the total amount of carbon. We also have to consider other aspects, like the fact that from Abrupt Thaw, we often see a higher proportion of emissions being released as methane. So this is not a pretty figure. It's just more of a sort of technical one from the work I'm doing. But what this is showing right now is the proportion from a little subset of models of carbon that is released from gradual thaw as methane. You can see it's a pretty small amount of that carbon that's coming out of methane. And this is the comparison for Abrupt Thaw, which comes out at around 20%. So you can imagine this does have a substantial consequence. One final point I just want to highlight, and it's something that will be talked about a little bit more later on, is that as with Abrupt Thaw, we can't just treat this as one issue to build into a model and then leave it alone. It also interacts with other processes, and particularly fire. And I think just this image sort of shows quite intuitively why we have to consider fire and permafrost thaw together. You can see this is a burned area, and you can just imagine the removal of the vegetation here, the darkening of the ground surface really changes how much heat is going into the ground, and you can imagine that having real consequences for permafrost thaw and including Abrupt Thaw. And there is a lot of work going on in this field at the moment. I wanted to highlight a finding just from one paper. This is just one example, which found that fire has a really substantial impact on particular types of Abrupt Thaw that we see happening in the region focused on here, which was Alaska. So just a little bit of a whistle-stop tour, just to highlight a few final points. I think the key takeaways here are that we can be increasingly confident we're seeing an increase in the incidence of Abrupt Thaw across the Arctic. And one of the core reasons for concern about this is the underrepresentation of this process alongside other processes in climate models. And work so far indicates that the implications of that are substantial. We do see when we make attempts to account for that, we see substantial consequences for our predictions of the future. And with that, thank you so much for listening. Very happy to take questions later on, and I'll hand over to our next speaker, who I think is Brendan.
Well, thank you again, everyone, for attending the session. Um, and just building on what Sue and Rachel have talked about, I'm going to talk about another process that is very important in permafrost zones, but is also not included in the models, and that needs to change. And so I'm going to be giving some updates about fires across the permafrost zone, looking at patterns, trends, and implications. I am a scientist at Woodwell Climate Research Center, which is on the land of the Wampanoag people. So I'm going to just start with some basics about fire. So fire globally can essentially occur in any terrestrial ecosystem, but we see that it mostly occurs in areas of intermediate moisture. So on the left side of this moisture curve, we have systems that we call fuel limited, or they don't have enough fuel for the fire to spread across the landscape. And then we have systems on the right, like the Arctic, that are generally aridity limited, meaning that they have fuel, they have vegetation, they have organic matter that can burn, but it's often too wet to burn. And then, of course, we need an ignition source. So humans ignite a lot of fires globally, but in the Arctic and permafrost regions, lightning is the biggest factor in terms of the fires that burn the most area. So we need an ignition source. We do get those two things in the Arctic quite a lot. So this is a map of cumulative burned area across the Arctic boreal zone, pretty equivalent to the permafrost zone for a 20-year period. And essentially in any non-mountainous region can burn at some point. So fires are an important part of the ecosystem. It's good to know that fire inherently is not a bad thing. These systems are adapted to fire. But what's happening now with climate change is that we're seeing dramatic warming. Oh no, another video that won't play. Sorry. This one's less complex, but I love this video. I'm sorry that it won't play, but good lesson learned. So essentially what it would show if it was playing was the time series of temperatures across the globe. And as you might imagine, as it progresses on and gets close to present day, the Arctic balloons up as this big red blob. The Arctic, the current assessment, the last assessment I've seen is that the Arctic is warming about 4 times as fast as the rest of the planet. So that is very rapid. And what that's doing in terms of fire, it's lengthening the fire season. So there's more time for fires to burn. It's resulting in more extreme fire weather. And it's also resulting in more lightning ignitions. So we are very much seeing intensifying fire regimes at northern latitudes. I feel like I give a talk such as this frequently, and my job is easy in the sense of updating from the last extreme fire season, because it seems like almost any year is an extreme fire season in one way or the other in high latitudes. This year is no exception. What I'm going to highlight here for Alaska and Canada is how the lengthening of the fire season has been taking place. So this is a picture of the Kwethluk fire that occurred in southwest Alaska in April. It's the largest fire in April in Alaska in 25 years, and it's virtually unheard of to have this kind of fire in April in the tundra. So this is really quite an anomaly. So the fire season started in April in Alaska. It was actually a very large fire season. It was followed by lots and lots of lightning, especially in July. But the fire season only just ended a few weeks ago. So in Canada, this is a picture of the Scotty Creek Research Station, which has been around for almost 30 years, applying lots and lots of great data. One of the first indigenous-led research stations in the world, and the fire came through and essentially destroyed all of the equipment. So our team is working to re-instrument the site currently. Looking towards Siberia, Siberia has experienced some really extreme fire seasons in 2019, in 2020, and in 2021. So this is a map. This paper came out in Science just last week looking at fires north of the Arctic Circle. All of those black areas are places that burned in the 18-year period, 2001 to 2018. And just in the 2 years, 2019 and 2020, you can see what burned, especially north of the Arctic Circle in Siberia. Here's another paper that also came out at the same time, just a different way of looking at it for the Siberian tundra. Sort of cumulative burning over the course of the season. Everything in gray is that 18-year period, and that's the last 3 years there in red and orange. So we're seeing a northward migration of fires into the tundra that really those systems do experience fire, but usually like they're not very frequent. They something hundreds or thousands of years, and we're seeing that happening quicker and quicker and quicker. And we do expect continued increases in burning with climate warming. Oh, good. So this video worked. So this is a map made by a colleague of ours at Woodwell, Greg Fisk. And what it's doing is it's representing projected warming across the Earth by mid-century as topography. So the red mountains that you see in the Arctic and the Antarctic are just representing how quickly that region is warming compared to the rest of the world. Where we have good long-term data, the whole thing seems jammed. Oh, nope. Hold on, sorry. Well, I can talk you through it if it's not going to play. But where we have good long-term data, we're seeing, and this is in Alaska and Canada, we're seeing about a doubling of burned area over the last 60 years. Oh, wow, my PowerPoint really did a number on this one. Sorry. I'm going to just try to get past this so I can continue the presentation. Okay, great. Let's move on. So the point is that it's been warming, it will continue to warm, and this is driving increases in fires. So I want to talk about the impacts of fires on carbon, building on both Sue and Rachel's talks. So again, wildfires are not a bad thing inherently, but we're seeing an intensification of the fire regime in lots of different ways. So fires can emit carbon in a few different ways. One of those is just directly the emissions that they produce at the time of burning. So most of the carbon that gets emitted to the atmosphere from fires in permafrost regions comes from the ground. So this is a picture of right after a fire in a black spruce forest in interior Alaska. And all of that soil organic matter, or duff, that you see missing is now in the air. So most of the emissions are coming from the soils themselves. However, and I apologize, I don't have a great picture of this, but what fires also do is they remove the organic matter, so that insulates the permafrost. So the permafrost can then start to thaw. So we see deeper thaw depth and deeper active layer thicknesses in ecosystems after fires. This is a graph of that, looking at different studies, but that increase in the active layer going from maybe a few centimeters up to almost 3.5 meters. When that occurs, that soil is then exposed to microbes that can decompose and emit both CO2 and methane. And as Rachael alluded to, in places with excess ground ice, fires can initiate thermokarst. So they subside, that ground ice melts, and that can lead to abrupt thaw processes that then release further carbon. So I'm just briefly talk through these three different ways in which fires emit carbon, what we know, and how that's impacting climate. So I would say we have the most information on direct emissions. It's perhaps the easiest thing to actually study. So myself and colleagues, both in Europe and Russia, have been building these databases of combustion measurements across the permafrost zone. And here you see a compilation of that for North America and Eurasia. The one thing I would note is the numbers. So we have many more observations in North America than we do Eurasia. So we need more observations, especially in Siberia. But we can take those observations, we can combine that with remote sensing, different types of modeling to get estimates of the amount of carbon leaving these systems through fire. We don't have the type of data that we need in Siberia, but we can build our observations into global models. And this is just the latest example of that, where we see a time series of carbon emissions from fire across the high latitude zone. First of all, just note the scale. This is a pretty high level of emissions. We're talking, up to 500 teragrams or half of a petagram per year. And the other thing to note here, 20 years is too short to really look at a trend. We probably need at least 20 or 30 years for fire trends. But one thing is that we tend to get, when we have large fire seasons in Eurasia, they tend to be low fire seasons in North America and vice versa, just the way that the climate system works. Looking towards the future, we don't exactly know what climate trajectory we're going to head on. We very much hope it's on the low end. What we can do, though, is look at all the studies out there that are projecting fire regimes and look at how that changes as a function of temperature. So this is work that we've compiled for some work that Rachael is doing. And, the dots are a little bit all over the place because they're using different methods and different studies, different regions. But look at the scale. So this is change in burned area, and you see dots well above the 250% mark. So we're expecting continued intensifications of these fires, potentially to large magnitudes. In North America, where we do have really good data, we can combine that with observations going back to roughly the 1960s and look at what we expect to be coming out from permafrost regions. This is Alaska and Canada from wildfires. And that's what you see as that sort of pink bar going into the future. This is showing gross emissions, so not accounting for ecosystem regrowth. Even if we build an ecosystem regrowth, and I should also note this is CO2. It's not methane or other greenhouse gases that are emitted, and it's also not accounting for permafrost. But the emissions are of the scale that's globally important. So within that pink bar on the right, for example, are the annual emissions from California. California, if it were its own country, would be about the 5th largest economy. So the emissions coming off these systems, even if you account for ecosystem regrowth, are globally significant. Also, as part of this work, we quantified how effective fire suppression is at limiting these emissions. It actually winds up being pretty cost effective in terms of keeping carbon in the ground. And then moving towards the impacts of fire on permafrost. This again is some of Rachel's work. Just want to highlight what's in the IPCC now that both Sue and Rachael talked about and what our models and observations are actually showing. So this is looking at the feedback in terms of gigaton CO2 per degree of warming. I should have a no tweet sign on this. I didn't realize to do that. But this is work in progress, so it's not published yet. So on the bottom left is the IPCC estimate of the feedback from permafrost in terms of remaining carbon budgets for humans to emit to stay within 1.5 or 2 degrees Celsius. From the models that we're using in the middle, looking at just gradual thaw, it's about double what the IPCC estimate. And I would say it's not just our models. Across the permafrost carbon community, it's pretty well known that what's in the IPCC now is very much on the low end. It's very conservative. But then when we build in what's labeled total feedback, this is both abrupt thaw that Rachael talked about and fire, we again get a doubling. So now we're looking at 300 or even more gigatons of CO2 per degree of warming. So these are very, very globally significant numbers. And this is a more complex version graph of what Rachael just showed. So nonetheless, looking at the 1.5 degree scenario on the left, 2 degrees on the right. And just to note the scale at which these emissions are projected to be coming out from gradual thaw, abrupt thaw, and then if you add in the fire processes, so direct emissions and then fire-mediated thaw. And to be frank, we also expect this number to grow because these are exceedance budgets. But we really need to be calculating our avoidance budgets. And those are different trajectories, and we expect permafrost to be emitting more in those scenarios. So my conclusions, I think, from a scientific perspective, certainly there are important science questions that remain. Nevertheless, we do know a lot. We know that fire activity in permafrost regions is intensifying and will continue to do so. We know that fire and fire-induced permafrost thaw impact global carbon budgets. That information is essentially not included in current estimates now. So as a result, we have some policy recommendations, including those emerging fire permafrost estimates into global carbon budgets, accelerating the ambition of NDCs. And I also think this offers us a chance to rethink how we do fire management, including restoring indigenous rights for cultural learning practices. Indigenous peoples have maintained these fire practices for millennia and are knowledge holders of deep fire knowledge, but are largely ignored from the Western management agencies. But also thinking about carbon and permafrost vulnerability as a potential metric for fire management and fire suppression. So thank you. Yeah, please, if there are any questions, we can pause. Oh, yes, please. We have a microphone to run over.
Hi, thanks for the great talk. I'm a graduate student from Washington University, and I study biomass burning aerosols that result from wildfires. So I'm really interested in your talk, particularly when considering carbon emissions. How much of that is carbon dioxide versus other forms of carbon like particulate, organic aerosols, and black carbon, brown carbon?
Yeah, so there are some pretty good estimates out there. I would say though that they tend to be biased by aircraft observations, which don't necessarily, for example, they're not getting the nighttime burning, which you have a lot of smoldering and more methane coming out. We do have some work where we're looking at the radiative forcing of all the greenhouse gases, and I can say, to a first degree, the warming from these fires, about half of it is coming from CO2 and about half of it is coming from all the other greenhouse gases. So it's not just methane, but it's precursors to ozone, N2O, et cetera. Aerosols is a really tricky one. It's not my expertise. From what I understand, of course, there's both black carbon, so there's again a carbon that affects the atmosphere, direct absorption, and can get deposited on ice and snow. But it can also result in cooling from increasing cloud nuclei. The estimates vary, but those, I guess, is one thing that I would like to push when understanding those, thinking about those forcings, is that the aerosol forcings, they essentially go away within a few weeks, whereas the greenhouse gas forcings, albedo, they last for a very, very, very long time. And the greenhouse gases are also globally mixed. So you kind of have to think about these in different ways. But it's also very important for, of course, understanding the effects of fire on climate.
Thank you.
Yes. So thank you. And the next speaker will be Gustaf Hugelius, talking about subsea permafrost. So thank you, Gustaf.
Hi, sorry,
Thank you very much. So now we'll be switching topic or switching domain to the subsea permafrost domain. So I'm Gustaf Hugelius from Stockholm University and the Bolin Centre for Climate Research in Stockholm. But I'm actually here presenting work on behalf of Paul Overdoon from the Alfred Wegener Institute. So I'm not a subsea permafrost specialist by heart, but I'm going to do my best in presenting Paul's work, a lot of which comes out of an ongoing EU project called Natali, which focuses on this domain on the border between the terrestrial and the subsea permafrost domain. So the subsea permafrost essentially acts both as a lid and a freezer on a massive amount of organic material and hydrates that are stored in the subsea system. I'm going to come back to and try to sort of tease these aspects out a little bit, but it's really doing us a dual service here. It's keeping already gaseous, especially methane, trapped in the seabed, but it's also freeze-locking a lot of organic carbon that is frozen in the sediments themselves. So it's acting as a lid and as a freezer. We'll get back to that later. So the sort of outline of this presentation, if we want to try to tease apart what are the climate risks associated with subsea permafrost. Is there a risk for immediate catastrophic methane release, as some past papers have at least alluded to? Or are we more looking at a sustained long-term greenhouse gas emission risk? And the sort of second part of this presentation, we want to tease apart what do we know? This is still a very data-limited area in general. Compared to the terrestrial permafrost zone, there's a factor 10 less observational data, and it's quite hard to study the subsea permafrost in general. So uncertainties are large, but there's also a lot of progress being made and a lot of new knowledge coming out. So we're going to look at how much methane and organic carbon lie beneath the Arctic seas, roughly. Can this reach the atmosphere in the form of greenhouse gases? And if so, when would that happen? So we're going to start with a map of the whole permafrost, the whole northern permafrost system, I should say. Here you see the terrestrial permafrost system in orange. Different colors, sort of shades, show you different coverage of permafrost from full to sporadic to isolated. And in green, bluish tones, you see the subsea permafrost system, which is essentially limited to the Arctic shelf seas, the areas where the Arctic Ocean are really shallow. And this coincides with areas where during the last ice age and preceding ice ages, when the water level was a lot lower, because a lot of the water was tied up in ice sheets, the whole sea level was lower, and these subsea permafrost areas that are now under the sea were at that time actually exposed to the air. So these are old terrestrial ecosystems that were flooded as the ice age melted during the last deglaciation, roughly 20,000 years ago and onwards. So we're really studying past terrestrial systems that have been submerged again by the water, and there's this sort of complex dynamic going on that we need to understand. You can also note that the size is roughly a tenth of the terrestrial subsea system, but it still holds a lot of carbon, which still makes it quite important. So if we zoom in on one sort of part of this system and look at a gradient from land to sea, this is from the Canadian Beaufort Sea coast. Here you see a cross-section across subsea permafrost system. You have the permafrost is in a blue shaded area, which overlaps with the red area that is the zone where gas hydrates are stable. And you see this zone exists both in the seafloor beneath the permafrost, in the permafrost, but it also exists on the really steep slope that goes out into the deep Arctic Ocean. So I'm going to get back to what gas hydrates are, but this is the system that we're studying, and it's actually thawing both from above and from below. The warm seawater is thawing it from above, but also often geothermal heat from the Earth's center is also thawing it from below. So what are the potential greenhouse gas sources from this system? The first one is the same as we see on land, organic carbon, old plant and animal remains that are frozen in the permafrost right now. And we find a lot of this wherever sediments or soils get deposited and grow. And in the oceans, you have both the old terrestrial soils that have been flooded, but you also have sediments that are just sedimenting in as in any oceanic system. So actually, this organic carbon in the subsea permafrost is like a sandwich with terrestrial soils, then marine sediment, and then terrestrial soils again, and these have added up over a really long time. And this as if this thaws, microbes will start to decompose it, which as a byproduct of their metabolism, they produce greenhouse gases. The other source of potential greenhouse gases that we find in the system are the gas hydrates. The gas hydrates are found both within the permafrost, underneath the permafrost, and in the marine system because of high pressures. So they're a little bit everywhere in the system, you can say. And if they melt or dissociate, they will become greenhouse gases directly. So gas hydrates, basically, they look like ice. So they are gas that is frozen into water, and they remain stable when they are either cold or under really high pressure. So that's why we have these different zones where they can be stable, both in the permafrost at greater depth, at the shelf, etc. And these are like concentrated methane bombs. So 1 liter of hydrate equals more than 160 liters of methane as it disassociates. And now I'm getting back to this concept of a pot lid and the freezer. So this is a complex graph that shows you a lot of different things going on at once. You have the permafrost zone as a sort of dark blue, and then you see in the red and yellow and orange colors, you have either free methane that's coming often from thermogenic sources, so basically natural gas. You have the hydrates, and you see how the permafrost is acting as a lid, keeping a lot of this trapped in the seabed. And then it's also acting as a freezer at the same time for the vast amounts of organic carbon that are in that system. You also see all of the process going on land that we heard about earlier with different landforms up on land. But all of this together forms like the full permafrost carbon feedback loop where you can have both the terrestrial system and the marine system releasing both CO2 and methane as warming progresses. So basically we have the pot and the lid, and what the warming is doing, it's cracking the lid and unplugging the freezer. And it seems like this is actually happening faster than what a lot of models had projected for the subsea system. And more and more observational data is emerging. This is a very nice example of sort of collaborative work in the Natali project, where researchers from Stockholm University have put together a circumarctic sediment carbon database. This is really the first openly available database that shows how much organic carbon is in subsea permafrost or in these sediments. A lot of this data was proprietary, belonging to oil companies. A lot of the data that still exists is often in the hands of oil companies rather other private entities. But they managed to put together a wealth of data, mainly with a lot of Russian sources coming into this database, and it's openly available for anyone to download and use. So using this data coupled to long-term models, researchers are now trying to figure out roughly how much carbon can have accumulated if you go to really deep down in the sediments. And the results are that roughly 3,000 petagrams, or 3,000 billion tons of organic carbon has accumulated over a really long time period. So over 450,000 years, when you have repeated ice ages accumulating carbon in the system. And that's roughly double the amount of organic carbon that's on land. Now, not all of this is gonna flux into the atmosphere, of course, but even if a fraction of it does, it's quite serious. Another paper that came out very recently that takes advantage of the new data becoming available has used a lot of deep sediment cores together with this Cascade database, and they found that the rapid ongoing annual thaw in the systems actually exposes more than 1 kilo of carbon per square meter and year to decomposition. That's between 5 and 10 times more rapid than what we see on land if you account for gradual thaw. If you look at abrupt thaw, it's similar. So this is also concerning when it comes to the potential future rates of release. And then when it comes to the stores of gas hydrates, so I just showed you figures for the organic carbon, the sediments, but the gas hydrates remain really poorly quantified. So basically, we don't really know how much there is. An estimate is around 20 pentagrams of carbon in this region from Rachael in 2015, but it's not known how much methane as free gas. Estimates of current emissions range from hydrates range between 0 and 17 teragrams of methane per year, a really wide range. For reference, the current growth rate of methane in the atmosphere globally is roughly 17 teragrams per year. So the whole growth rate of the whole sort of methane budget is on par with the highest range of estimates here. And it's believed that 17 teragrams for methane alone is probably an outlier and not really what we're seeing today. It's probably closer to 0. Or 1 or 2. But there is, with that said, there is a lot of evidence for methane emissions. Observational evidence of seabed features, like these sort of potholes in the seabed and bubble plumes that we see that are associated to methane release, either from from bubbles accumulating from hydrates or from the decomposition of organic sediments, or quite often actually from geogenic sources, so natural gas seeps that are bubbling up. As the permafrost is thawing, more and more natural gas can reach the atmosphere in the form of bubbles. So then the question is, how quickly might this happen? Permafrost thaw is needed, and then in that case, permafrost thaw will make organic carbon available for decomposition. And then the question is, how much of that can come out as methane? How much of the free gas and hydrates can be emitted to the surface? This is a really complicated problem because most of the methane that is formed in the seabed is actually not reaching the atmosphere. A lot of it is oxidized in the sediments or oxidized in the water column, or not just reaching the atmosphere themselves. It stays in the ocean. I think there's a general consensus that the sort of methane bomb, really rapid emissions that have been alluded to in early literature, there's no evidence of that, and it's unlikely that that is something that's going to happen on very short timescales. With that said, this is still a very serious issue for longer timescales. This is the recent modeling work on subsea permafrost thaw, one of the first coupled models to really be able to include subsea permafrost thaw in a good way. And what you see here are the sort of what's called the rocky road is RCP 8.5, and then you have middle road, RCP 4.5, and the green road or the blue road, or whatever you want to call it, RCP 2.6. And you see there's a massive difference in the thaw rate when you go to the 8.5 scenario. And this appears to be driven partly by couplings to the sea ice extent. So when you get less and less sea ice, you also get a more rapid thawing of subsea permafrost. This is still being delved into the exact connections there, but it probably has to do with brine formation under the sea ice that links to the vulnerability of the subsea permafrost. But where does this happen? As you see, these are maps that shows you from the left 2.6 out to 8.5, and you see that most of this thaw is affecting the Siberian shelf systems, where also a lot of this carbon is stored. And it's not happening super rapid. This, if we go back, you see this really high thaw we see around year 2100 and progressing to 2300. But still, within 100 years, we might see a very rapid thaw of these systems. And then if we take this one step further from permafrost thaw into modeled degradation of organic carbon becoming available for microbes, you also see these quite high levels of organic carbon being degraded in the sediments themselves. And now I talked about that this is really difficult to actually transfer into emissions. So this is also from work in preparation in the Natali project that I mentioned before. But sort of early model results show us that we might be looking at actual methane emissions if you account for the oxidation in the water column, how much of it stays in the water, what reaches the atmosphere, etc., of anything between a few teragrams of methane per year in the sort of lower end scenarios up to something around 20, even 30 teragrams per year in the higher end scenarios. So then the subsea permafrost alone would actually outpace the total growth rate of methane that we're seeing right now globally, which is 17 teragrams. So that's a really concerning scale of magnitude for this. But there are really large uncertainties. It's difficult to know how easy it is to decompose the organic carbon, because methane production and consumption is very sensitive to the organic matter type. So we need to know the sediment types. How permeable is the sediment to gas? That is also something that is relatively poorly known, but very important for the model output. And how effective is the methane oxidation or consumption in the sediment and the water column? These remain really large uncertainties, which means that these numbers that I just showed should be taken, as indicative, but still early days. So then the question is, do we see any of this, this methane already in the atmosphere right now? And the short answer to that is no, not yet. There's no strong evidence that subsea methane is really reaching the atmosphere in quantities large enough to be duly detected in global methane budgets. But we probably will in the future, or we surely will if warming keeps going as they are right now. And sorry, that was sort of my end and my take-home message with this talk. So I guess I will hand over.
Hi, so thanks so much to all our speakers. We'll have a Q&A session now, so if our panelists could come to the front, I'll hand out a mic for anyone who would like to ask questions, and they'll have a mic to answer.
Hi, thank you very much for your question. My name is Rebecca Topé. I'm with the government of Yukon, and I was just wondering, how does the subsurface permafrost actually get released or melted? Like, what would make it do that? Or do you know?
Yeah, now I have to turn the mic on as well. Yeah, so it's essentially the warmer water temperatures that are causing it. And it's also important to note that when you have when there's a high salt content, the water or the permafrost can actually be thawed, it can be below zero but actually still be liquid. So there's also this aspect of really briny, salty water doesn't actually freeze at 0 degrees, but it remains liquid for a little bit longer. So there's also those dynamics. But it's essentially, when it's a top-down thaw, it's warmers the bottom waters, which then have a strong feedback to sea ice and other processes at the surface. And that's also why we see the most rapid thaw happening close to the coast, where there's mixing of the water column, where warmer surface waters can reach the bottom at some parts of the year.
Thank you, everybody. So there's been a number of papers in the last few months about intermediate water warming. One paper was how intermediate depth water was melting glaciers in East Antarctica much more than expected. It was undercutting it, and the freezing point of seawater at the bottom of the glacier was about -3 Celsius. And there was another paper in the last few months about methane cloth rates being thawed near the equator off Africa. So it's not just in the Arctic that we have to worry about the cloth rates. So this intermediate water warming, which is actually quite large, it has huge effects globally, and if it's not considered, I'm sure it's not considered in the cloth rate models for how much melting there will be. So I don't know. Do you have any comments on that?
No, that's unfortunately quite far from my expertise. But as I mentioned earlier, I mean the synthesis of potential cloth rate emissions that are available for the Arctic system are quite a few years old now. So I would, those estimates definitely did not include sort of more recent observations on water column dynamics. Although I mean, there are ongoing modeling efforts where newer oceanic models would resolve the type of processes that you are talking about, and observations of intermediate. I mean, there's a really strong interest in those processes because, as you mentioned, they are undercutting ice sheets and speeding up the thaw of shelf ices in other systems. So there's a large community working on improving modeling of those dynamics, but I don't think I can comment beyond that, unfortunately.
Thanks for the great talk. As Arctic surface sea ice summer extent continues to decrease, there is growing interest in deep sea mining and extracting oil. So what would be the impact of these activities on subsea permafrost? And has there been any study on that? And my second question is, what kind of observational data do you use to make estimates of the extent of subsea permafrost and the emissions from that?
Thank you. I think oil and gas extractions definitely have a local impact, and just when you drill through the permafrost, you will often get quite rapid catastrophic release of any methane that was in the system. Usually they would try to capture that and burn it. I don't know to what extent that is successful in. So I mean, the companies that are doing the drilling or whoever is doing the drilling would try to, if there's massive methane leaks, they would try to capture it and either use it or burn it off. But it definitely has local impacts, and you will definitely be disturbing the system locally. And I think the maps of extent that I showed, the most recent map that I showed you, the most recent map available is the one that I had in this presentation, which is basically a combination of borehole data with measurements of permafrost temperatures going back several decades, and then you use the sort of the evolution of the temperature in the borehole itself tells you something about the age of the permafrost in that area and the progression of thaw, and then that is in turn coupled to models that run both over shorter timescales but also run over multiple interglacials, so that they actually model it with a sort of low resolution climate model that is able to run over a very long time and capture these dynamics of the shells being exposed and then retreating again, and the model then tries to calculate the thermal properties of the sediment and the soil and then model the distribution of permafrost from that.
Okay.
This is a more general question for everybody. Can have a go at it. So as a specialized academic, studying a glacier or studying one component of the climate system, do you actively try to spend at least a bit of time each week figuring, studying, you're studying a different aspect which would be related to your work? Like the question of the intermediate water is vital for the cloth rates. The wildfires, studying a little bit about droughts and rainfall patterns and stuff would be vitally connected, but not directly in your field. So what I'm trying to say is we need more scientists to become a little bit more system oriented, how their work relates to other people in other fields, and because that's the only way we're going to join all the dots on what's happening. And we need, it's as people are not listening so much to hardcore science stuff, but if you translate it into everyday language, which is part of what you're doing with presentations, but the talks you would each give would be to your colleagues at university or other universities, not to the public. So do you ever consider going out to a public library and talking about the whole climate system? Because James Hansen's talked for years about scientific reticence as being one of the major blocks to getting the message out. I mean, we're all living on this planet, and it's just going to hell, really.
Is it on? No, it's on. Okay. So I think I'll answer I don't know if I captured everything, but the first part of the question about do I study other areas that are unrelated? Not as much as I should. I actually don't even have the time to study the areas that I think are related. So, like, no. I also think there's a challenge in that though, because if it's unrelated, like I may not know what's related, right? Like, where's the areas where I should go to study to connect to this? The one place that I would say to go is for Western scientists to have more conversation with indigenous knowledge holders, because their way of knowing, their understanding of seeing the world does bring those things together already. So there are climate scientists who are indigenous knowledge holders who have this perspective of the interconnectedness that I think is probably a more effective way of gaining an understanding of the components of the system that we should be looking at.
Yeah, and just to echo that likewise, I think one thing I've really learned from Indigenous colleagues and Indigenous collaborators is to see or attempt to see the system more holistically than we're trained to as Western scientists, which is a kind of ongoing learning process and challenge. But I completely agree with you. It's a really important one. And on your second point about, which I think is about sort of taking scientific information and knowledge to different audiences. Like, again, I could not agree more with that. I've actually, some of the most kind of enjoyable and interesting speaking experiences I've had have been at places like music festivals or churches or in museums, and to perhaps groups of people who are there for a very sort of mixed event, interdisciplinary, cultural, arts focused events. And I think that's really important. Again, it's something that I think we're not trained to be comfortable with as Western scientists, but I think it's really important, and it's something, again, that I've learned a huge amount from, both as a communicator, but also just as a scientist. What are the questions that people are interested in? What are the things that people know and do not know? It's been, so I agree. It's really important.
Maybe I'll just build a little bit on what they said. Definitely want to echo the indigenous knowledge that is held does not, as was in the previous session, break the world apart into these silos. I think we have a lot to learn from them, not just about how the world works, but also how humanity can live in harmony with the planet, which obviously is not happening now. And just as far as science goes, I mean, I do see a general progression over the decades from these very distinct disciplines to more interdisciplinary work. I personally was privileged to be in a PhD program, Earth System Science, and so we studied the oceans, we studied the atmosphere, we studied the land, and I think more programs like that need to exist for people who are going into climate science. And I also just think that what's really important, even as Sue mentioned, if we don't have the time necessarily every week, but for scientists, for anyone really, to just remain open to learning, right? So if you stay within your knowledge silo, you're not going to expand out of that. But if you take opportunities like this conference, like other like talking to people from different backgrounds, different scientists, but also just people from different walks of life, you can learn every day. And so I think we need to be open to continue to grow and not get stuck in we are the experts of our particular field, and that's just the way it is.
Yeah, I think I can just agree with the previous speakers, and I think that we don't broaden out as much as we should probably. With that said, there are some scientists tend to specialize in being synthesis scientists, so that really take an umbrella view, while others are really focusing narrowly on their expertise. So I think that there are scientists that do take this broader view and that have the time to do it. But probably more of us should be doing it and should be doing more sort of public outreach.
Hi, do we have any other questions from the audience? If not, okay. Well, great. Then thank you guys so much for attending this panel discussion, and thank you to the panelists for all the wonderful information that they've provided us. So with that, we'll be concluding this event, and the next event will begin at 1, called Intergenerational Justice in the Runway Train of Committed Permafrost Emissions. So thank you again to all our panelists.